Okay, here we go. So some of you may have noticed on the quiz yesterday, there's a problem that was written in a notation where it had a 1 and a 3 above the squiggly integral symbol. Yeah. But you figured it out, right?
Yeah.
That meant going from 1 to 3. Okay, good. And so what we've done already is we started taking areas under curves and breaking them into rectangles. We had a delta x value. That delta x value was true across the entire thing. So that was b minus a divided by the number of rectangles, gave you that delta x. Today we're going to do two things. We're going to talk about this guy named Reimann, and we're going to figure out what a definite integral is. And this will get the ball rolling. Not too tough today. So we're talking about a Reimann sum, who Reimann is, and what he basically asked one simple question, which we'll get to in a second. We'll talk about what a definite integral is, using limits, because some of you mentioned yesterday, well, if the width of the rectangles get really small, or the number of rectangles gets very big, wouldn't that give us a more accurate answer? The answer is yes, and that, of course, sounds just like a limit. We'll talk about some properties, that's easy peasy. And then we're going to do some geometry today. My favorite. Yep. Okay.
I remember those days.
Good old days, right?
Where's the fun one?
All right, so Reimann. Reimann says one simple thing. Well, I'm not going to tell you what Reimann said. I'm going to ask you a question first. What's that mean? All right, how about a picture? Okay, there's a picture. What's delta x? How is delta x represented in that picture?
It's different
It's different.
What do you mean it's different?
every time.
Yeah, you're the one that said it. What's different? What's it?
The width.
Whoa, sorry.
Oh no, the width of them gets larger, or larger and then decreases again.
Okay. So the yellow, the blue, the green, and the red rectangles are all different widths.
Yeah.
Is that a problem? It could be. But then again,
Get out of hand.
it might not be.
Maybe like this strip where the slope is the smaller the width of the rectangle, or like the other way around too, because like the yellow is the steepest slope, there's the smallest, but maybe that would.
Okay. So let's go back to the notation. What does delta x represent? What has delta x represented up until this point? The width. Now the problem is we've got different delta x's, right? Question, statement?
Maybe it could be the width in relation to the slope of the tangent line if they're given.
Let's see what happens. What's f of c? Or in fact, f of ci. There's no c in that picture. What does c usually represent? Constant or some number, right? So what's f of c?
Some constant.
That's doing everything in my power not to give a smart aleck response. Yes, Paul, that's correct. And what would the f of some constant how would that be represented in this picture?
A y value.
Good. It's a y value. So what is f of ci times delta x? Of a rectangle. A rectangle or the rectangles? Not quite. A rectangle, and then what's that squiggly looking thing out in front? Sum. Do you know what that thing's called, by the way? Not the It's a sigma. That's a capital sigma. But the sigma does mean that it's a sum. And we're taking a sum. The notation on that means going from 1, when I equals 1, up into n, which is, in our case, probably a pretty big number. It doesn't mean at 1, it means for the first rectangle. So in this case, what would n be in this picture? 4. Good, there's 4 rectangles, we're going to do it 4 times. Start with the first rectangle, the second rectangle, third rectangle, fourth rectangle. That's a fancy way of saying the area of all those rectangles added up, and we've been doing that for 2 days now. So delta x is the width of one rectangle, it's the height of one rectangle, the sigma is the sum of all those rectangles. Okay? Still a bunch of wasted space in this problem. Just as a review, is that function increasing or decreasing? Increasing. Are those left hand, right hand, upper sum, or lower sum rectangles?
Right hand.
Very good. Right hand, I almost just directly contradicted what you said. Yes. Right hand and upper sum rectangles, because the function is continuously increasing, that stays true for all 4 rectangles. Okay? Any problems? All right. And we already noticed that. So Reimann said one simple thing. Why do the rectangles have to be the same width? And the answer is they don't. And because they don't, he becomes famous, and like all mathematicians, he named it after himself.
So conceited.
God, they're egotistical, maniacal idiots. These math guys, you can't trust them as far as you can throw them. All right, so we want to start talking about the idea of a limit now. I'd like to decrease the wasted space above the function and get it as close as possible. And I showed you what that looks like the other day when you decrease the width of the rectangles or increase the number of rectangles. Everybody with me?
Yeah.
Beautiful. So we do a limit, and we can do a limit thinking of it 2 different ways. We can either increase the number of rectangles, or we can decrease the width of the rectangles. And in this case, it would be easy to decrease the width of the rectangles. So to get an exact answer, how small would I need those rectangles to be? Very small. How small? Infinitely small, also known as?
Negative infinity?
No, not that small. No, that would cause the universe to cease to exist. 0. Now, what goes to 0?
The x.
Delta x, right. But there's different delta x's in this picture. If I want to guarantee that all of those rectangles disappear to a width of 0, which one am I most concerned about? Do you understand the question? I'm going to shrink each one of those rectangles. I want them all to go down to 0, and they're all shrinking at the same rate. If they're all shrinking at the same rate, which one am I most concerned about? Yellow, blue, green, or red?
Green.
Why green?
Because it's the biggest one.
Okay, everybody good on that concept? If I take the biggest, fattest rectangle, and I shrink that down to 0, if all the other smaller rectangles are shrinking at the same rate, then by the time the green one gets to 0, the other ones have gone to 0. You follow me?
Yeah.
Ya follow?
I dig.
Cool. So that's what Reimann said. Reimann said, all right, let's forget about this rectangles being the same width. Let's make them all kinds of different widths because they might fit better in the picture. This one doesn't fit better, but it's an example. And then if I just take the biggest, fattest rectangle and shrink it to 0, then all the others will shrink to 0 and I get an exact answer. Okay? Now, that biggest, fattest rectangle is what's called the norm. Yes. You just wanted to relate. Is that the only norm you know?
No, I was confusing Norm with Gordo for a second.
What?
And so I was like, why?
Yeah, Norm was on the movie Cheers, or on the show Cheers. No, never saw it. It's beyond, it's before your time. Yeah, so you know anybody, what's the show where the people have died and they've gone to heaven? The Good Place. So the guy that plays the silver-haired guy on that show was on the show Cheers when he was about 25.
Wait, the old guy with the glasses?
Yes, Ted Danson. Yeah, it's when he was young.
I love
All right, so, sorry, I got sidetracked
I
there.
love that show.
We've got these regions here called partitions. Right? And all the partitions have different sizes. So if we just take the biggest, fattest one, the norm, strangely enough, Norm on Cheers was a big fat guy.
See? That's what she said.
Interesting.
But no, but I thought I was confusing with Gordo.
He'd stand by me.
Instead of me.
Yeah.
Yeah.
Okay. If we shrink that down to 0, then we'll get an exact answer. So here's the notation at the very bottom. This was a summation that we talked about on the last slide. That's the area of all the rectangles added up. Now I want to take a limit as I start shrinking those rectangles. And if I pick the biggest, fattest one, which, again, the notation is a delta with two absolute value bars around it, if I shrink that down to 0, then that guarantees all the others shrink to 0, and we get a bunch of segments that, when added all up, give us the exact area. Are you okay with the concept? Yeah. Now, the process of doing that is way ugly. So, we're not going to do it. Okay? What is important, however, is that you understand what Reimann was suggesting. And he just said, I don't want them to be the same shape. I want them to be pretty colors and different sizes. Because all sizes are beautiful. Right? But I'm going to take the big fat guy and shrink him down to 0. Okay? That's not practical for us. It's just like when we did derivatives. We had a formal definition of derivatives and then realized this is a waste of time. Isn't there a better way to do it? And the answer is yes, there is a better way to do it. We're just not ready for it yet. Okay? Any problems? Any part of that that's not clear? We're solid? Great. So, definite integral. We've done indefinite integrals. When we do indefinite integrals, when you take the antiderivative, you get another function. We want to get numbers. And that's called a definite integral. That will give us the exact area under the curve. So there's the fancy definition. Now you can write this down, but you don't need to, because we did this already. You know what that mess on the left-hand side is. And the only thing that's new on the right-hand side is we stick an A and a B above it. Well, above it and below it. And all that says is, I want the area under the curve from A to B. Or not to B, that is the question. A little bit of Shakespeare for you this morning. You're welcome. The most important thing to remember out of that picture is that A is the starting point, B is the ending point. And the terminology there is lower limit and upper limit. Lower limit is where we're starting, upper limit is where we're ending. Don't get that confused with upper sum and lower sum. They're different. Okay? Any problems? Easy peasy? You're wondering what a problem looks like, right?
No.
Yeah. In order to solve those problems, we need something called the fundamental theorem of calculus. Yeah, we're not ready for that yet. Oh, it's a guppy lesson for sure. We'll get to that. You know what a guppy lesson is? That's when everybody sits there like this. You know, like guppies in a fish tank. What's that?
When that was showing up on here, that would be awesome.
All right. Let's talk about the properties. I don't want to spend a lot of time on these because they're the same properties we've had all along. Like, the integral of a sum is the sum of the integrals. That kind of stuff. So here they are. Sum or difference of an integral is the sum or difference of the integrals. I think I said that right. Okay. If you got a constant out in front, you can move the constant out in front. Notice there's no multiplication and division here because there is no multiplication and division for integrals. And then, why is it's off a little bit. It's a wee bit wanky. Could you explain the bottom one to me, please? Why is the integral from a to a of some function in terms of x equal to 0?
There's no way. It's just line.
Good. Everybody follow that? Yeah, we're going from a to a and it has no width. The rectangle is already shrunk down to 0. So you're trying to find the area of a segment which has no area. That doesn't come up very often, but occasionally it'll show up. Okay, so this is a big one, however. And this is better explained with a visual. Can I place this here? Okay. Let's suppose I want to find an integral of this curve, whatever that is. And I want to go from A to B. Okay? I want that area. So here's f of x. And I'm going to go from A to B. Okay? Which is what this says here. you probably could have gotten this without the picture, but I think it helps if you see the picture. It's saying, instead of doing one big region like that, I can just split it into multiple regions and get the same results. So I could chop it, let's say, here with a C-term. Now I find the area of this guy, I find the area of that guy, and add the two up. Make sense? And you did it. Yes, sir.
Can you do that more than once?
Great. I was just going to ask that question. Could you ask that question again so everybody can hear you?
Can you do that more than once?
What's the answer to his question?
Yes.
How many times could you do it? An infinite. It would be a waste of time, but yeah, you could split. And you did that on the quiz yesterday. That last problem on the quiz involved a triangle, a weird rectangle with a semicircle out of it, and a trapezoid, or you may have done the trapezoid as a rectangle and a triangle. But again, taking the shape looks something like this. Yes?
Yes.
Okay, so I'm assuming you did something like that, and who did a trapezoid?
You didn't need we didn't need the triangle part because it only went from 0 to 6, but the range was from 0 to 7. So the triangle part
You didn't-
wasn't part of it.
This was no good?
That wasn't part of it.
Oh boy, my answer key's wrong then.
No,
I
it's
didn't
right.
see that.
Oh.
Yeah.
I didn't see that either.
I think your answer key's right.
I should run my own quiz. Whoopsie. Okay, but anyways, got the idea?
I'm pretty sure I was right. It was really 6.
Whoa, 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 whoa. The second one is also very important. Relax. What's happening in that last statement?
It's going from A to B.
It's the same, but maybe,
So it's
Why?
not going from this
because it's going, instead of going from like left to right, it's going from right to left.
Perfect. Now, is anybody bothered by that? So I'm gonna, if I go back to that picture that I just erased, I'm gonna find the area under a curve, and my answer is gonna be negative.
But it's the same.
Wait, what?
No.
I'm a little confused by it, I guess.
Negative area.
I'm a little uneasy.
Negative area.
I'll find a little bit.
You just made it work.
Yeah, I know he did. Do you understand what this is saying?
I mean, I get it.
Okay, you get it. So instead of going from right to left, if you want to flip it back,
Oh, yeah, 'cause just.
you just put a minus sign in front. Okay, so this is okay. What you don't like is Paul opening his mouth and saying things like negative area. Yeah, that,
Paul, it's all your fault.
yeah, Paul, stop talking.
Confuse me.
Okay, let's look at an example, and then I'll come back to this stuff that he's talking about.
What's going on with that?
I don't even know what I'm talking about.
With what we know so far, there's 3 statements up there. We could find the last 2 using geometry, right? What's the curve, what's the graph of x look like? What kind of line?
Straight line that's always increasing,
Outstanding. Keep going.
that goes in either direction and is continuous and differentiable at any point.
Look at him pulling out all the big guns.
You just did it.
Don't know that. You start figuring out everything you know.
Is there anything else you want to rattle off there? Like what you had for breakfast,
It's
or?
also rational, probably.
Okay.
It's over one.
Uh-huh.
I didn't say it was continuous.
Could you tell me what it looks like?
Both theorem applies.
And don't say a line.
Diagonal line doesn't. Passes through the origin.
It does. We're getting warmer. Anybody else?
I'm lost, man.
It's a vertical line.
It's not a vertical line, it's a 45-degree line. Y equals X. Okay, so we're talking about this guy.
Vertical line, 45 minutes.
There's my graph. And if I want to find the area under the curve from 4 to 2, or sorry, from 2 to 4, here's 2, here's 4, could you do that?
With the triangle.
Not a triangle. It's a trapezoid.
Oh.
which you could break into two, if you'd like to, you could do a rectangle and a trapezoid, or a rectangle and a triangle, or you could do the trapezoid. But you could find that area, right?
Yeah.
Okay, good. Where's this point?
Half of two.
2.
That.
Where's this point?
4.
How long is that?
4.
How long is this?
2.
How long is this?
2.
Therefore, the area would be 6, right? Because it says right here, 6.
Yeah. Yeah.
All right, so we can do that, yes?
See.
Bien, gracias. Now, what about this little bugger? Could you find that?
On a good day.
This one might be a little bit more challenging. What does the graph of that look like? Oh, by the way, what is that? Doesn't it appear that there's no function there? There's a 1 there, very good. Maybe this will go better than I thought. What's the graph of 1 look like? It's a horizontal line. Could you find the area below this horizontal line from 2 to 4? You bet you could. It's a rectangle. How wide's that rectangle?
2.
How tall is that rectangle?
2.
Therefore, the area is?
4.
It's wide.
Oh, wait, slow down. 2 times 1.
Use your calculators if you have trouble with that. I put a program on there called multiplication. Could you find the one on the far left, though?
Draw it out.
Using the new stuff.
You do it for us, yeah.
If I do it for you, the correct answer is no, you can't. We could approximate it using rectangles. We could approximate it by using Reimann sums and making it, but we can't get an exact answer yet. That comes later. Okay. And that's what the nature of the beast is, being able to find the exact area given just a function. Okay, so I wanted to do this for 2 reasons. Number 1, it gives you an idea how to find definite integrals using geometry, trapezoids, rectangles, triangles, that kind of stuff. But I also wanted to show you that we can't do that yet. But it does allow us to find that. That's a long-winded way of saying we can evaluate that by just using the properties of definite integrals. Okay, so before we do that, graph that on your calculator, please.
Oh my God, what did you say?
Okay, got a picture of it?
Yes.
All right, good. We'll come back to the picture in a second. Eventually, we'll be able to find this definite integral using purely math. But for now, we have to figure out a different way to do it. The different way to do it would be to simply split it into parts that we know how to work with. So, for instance, I can rewrite that this way. One of the properties was we can move a constant out in front. So if I move it out in front, I get 10 times the integral from 2 to 4 of dx.
Okay, word.
Move the 4 out in front, we know how to find the integral of x dx because I told you it's equal to 6. And then the last mess, we don't know how to find yet, but I just told you it's equal to 60.
Oh, you can break it up like that.
Sure you can.
What even is this?
Oh, that makes sense.
Are we supposed to be one of those?
I'm sorry?
I don't know this function.
Yeah.
That's the problem.
Oh, okay.
The first line is you're given information, which you need in order to evaluate. At this stage, eventually you'll be able to do this without.
I don't get it. You're plugged 2, 6, and 60 in for
Because there's always a.
Oh, the
X.
I thought I guess you.
All right, let's go back to this. Paul, what's going on there?
You're distributing the integral side, I guess.
Is anybody bothered by the answer?
There we go.
It's a negative area. Look at your graph now. What do you think?
Under.
What do you think that negative area represents, Amanda? Under 0. What do you mean?
Like black.
Good. That's the area. Well, that's the total area. And it's the area below the x-axis. Okay, so this kind of defies what you did in geometry. And that in geometry, you knew that if I asked you to find the area of a trapezoid and you told me the answer was -8, I would laugh at you and make all kinds of snide comments right to your face.
Wow.
In this class, however, we have something which is considered negative area. And how is negative area defined? Negative area is defined by any area that's below the x-axis. Below the x-axis, negative area. Above the x-axis, positive area. Just because your answer is a negative value doesn't mean the whole thing is below. It just means that there's a chunk of it below. For instance, if we were to solve that definite integral, well, hold on. What would this be as a definite integral? What would... I like how you wait like 45 seconds before you say what. You know what I'm talking about? What? What is this problem as a definite integral? From what to what? -2 to 1 is a good start. What are we taking the antiderivative of? 2x. What am I missing? dx. That's all I was asking. What's that equal to? Will my answer be positive or negative?
Negative.
Why negative?
Because it's more graph under.
Good. Okay. Depending on who you had for geometry, or how well you learned geometry, you may have forgotten some of those things. I want to assume that you know the area of a triangle, but you know what happens when you assume things. Yeah, boy. I assume you know the area of a circle.
Don't. You know what happens when you assume?
Yep. We covered that already.
Yeah.
Stay with the lesson. will you?
I'm sorry.
And then the area of a trapezoid might also be helpful. If you don't remember the area of a trapezoid, then break it into a rectangle and a triangle. That's perfectly fine.
When did you start saying trapezoid?
And then parabola.
About 15 years ago.
Parabola.
I started.
What's best is when I mispronounce words, and then years later, Bridie comes in and yells at me because his juniors in pre-calc are using the word wrong.
Yes.
Oh, yeah.
Yeah.
No, but he says something great too.
Well, if you go to the real world, that's a parabola. People are like,
A parabola, trapezoid,
Yeah.
isosceles.
Well, Brian,
Maybe
misses
twice a
it.
year.
Parabola.
That's a graph.
Alright, so, we'll wrap up with this. Based on the work we did in the previous problem, could you find the answer to A? What does that function look like? Horizontal line. So if I want the area under a horizontal line from 1 to 3, what geometric shape would I get? Outstanding. Okay, what's the graph of x plus 2 look like? A line? What kind of line? Don't tell me a straight line. All lines are straight. It's a diagonal line. Good. If I look at that diagonal line from 0 to 3, what geometric shape would I get? Trapezoid, correct. Not a triangle because it doesn't pass through the origin. Last one.
That's so bad.
What shape is that?
Semicircle.
Top, bottom, left, or right?
Right.
Right top.
Top. What's the radius? Anybody see that?
Yeah.
A piece of fudge just flew out of my finger. Where did that come from?
What?
Fudge. You
Say
really
fudge.
Say fudge.
I heard fudge.
Where did you get fudge?
A piece of lint.
Oh.
No, I said fudge, not fudge. That would be really weird if a piece of fudge just flew off my finger. I haven't had fudge in like 25 years.
Fudge is so good.
Wait, it is. Yeah.
Oh, yeah, okay, so it's a semicircle, it's the top part, what's the radius?
What? I just came
2, can you find the area of a semicircle? Outstanding. Rectangle, trapezoid, semicircle. Okay, you ready for this?
Okay. Ooh, double
Absolute no.
There's two triangles.
Oh, no. Double triangle.
What if I wanted you to find the integral from -3 to 2 of the absolute value? Number one, we can't even take the derivative of an absolute value. Do you think we'd be able to take the integral of an absolute value?
Absolutely not.
Absolutely not. There's probably a way, I just don't know how to do it. But if you draw a careful picture, you see that we break it into 2 triangles.
Can you go back 2 slides, please?
What? That one?
Yeah, thank you.
You're welcome.
Oh, it's the area, but trapezoid. No,
Trapezoid.
trapezoid. No.
Good? You need this one too?
No.
Okay.
Zoid.
All right.
Zoid.
So, this is basically the quiz problem taken to a next level, being able to graph that and then break it into 2 triangles. Notice that those triangles are not congruent because it's not symmetric,
But that falls.
but you should all be able to find the area of 2 triangles. Add them up, we're good to go. Any problems?
No.
Okay, so eventually probably being tomorrow, we're going to talk about how to do these without drawing pictures, without relying on the geometry. And again, that thing's called the fundamental theorem of calculus. It's not that bad, but it can get a little bit nasty. Now, here's the other thing to be careful of. The calendar, which many of you use for homework, is not accurate for us. We're a couple days behind. So notice the homework is day 60, not today's homework. They're on day 60. Okay? Questions, concerns, anything for the good of the cause? All right, wait, we're not done yet. Hold on. Get out your calculators now.